So we're going to kind of switch gears here for a moment. We're going to talk about concentrations of solutions. So as I said in the beginning of this whole module, it's that we usually do things dissolved in water as the reaction. You don't put a solid with a solid and react it. It's usually dissolved, and then that's when we have a reaction happen. So we're going to get more into those solutions. So what this is about is the concentration of a solution, because you can't just throw a specific amount of stuff into a solution and expect it to do what you want it to. You don't know how much is in there. So quantitatively, I need to know how much stuff is dissolved. So that's called the concentration, or the amount of the solute in the solution. So concentrations mathematically, quantitatively are going to be important when we're doing chemical reactions. So the concentration unit that we use in chemistry is molarity. So if I ask for the concentration of something, I want it in molarity, unless I specify otherwise, but usually I want molarity. Okay, molarity is a capital M. So when you're writing out the answer, you would put the number, capital M, and then whatever it is that's dissolved. Okay? So the definition of molarity is the moles of your solute per liter of solution. Okay, so how much stuff is dissolved in this liquid that I have. Okay, so I might ask you, how do you make a solution of blank? Or in the lab, you might have to make a specific concentration. So if you're starting with a solid, this is what you are going to do. You are going to add your solute, or you're going to weigh out. In this case, I'm making a copper sulfate solution, so I'm going to weigh out however much I need. Now, molarity is in moles of solute, and of course, we measure in grams, so you do have to do a little math there to figure out how much, but in this case, I needed 39.9 grams of copper sulfate. Now you put that solid into what is called, this flask right here is called a volumetric flask. This is a very specific type of flask that we use when making solutions. So anytime you need to make a specific concentration, you should use a volumetric flask. Now, what size depends on how much you want to make. If I want to make 250 milliliters, I use a 250 milliliter volumetric flask. If I want to make 50 milliliters, you would say put in a 50 milliliter volumetric flask. They have all kinds of sizes, but you have to make exactly what that volumetric flask is made for. Okay, so you can't use a graduated cylinder. Volumetric flasks are actually very precise, and that's why we use them for solutions. So like this is a 251, and it has a line right there, can't really see it, but there's one line indicated on this, and that is the 250 mark. So you put the solid in there, you add a little water to get it to dissolve, and then you add water. You would just say fill to the line with deionized water or distilled water, and then mix, and that is it. So weigh your solute, add water to the line in whatever size volumetric flask, and then mix it. And you can invert these, you put a cap on it, and you invert it. Okay. So volumetric flask is kind of the important takeaway there. If I ask you how to make a solution, you should be able to tell me how much stuff to weigh, what size flask to use, and then you would say just fill to the line. Now, types of problems I could give you involving concentration, I could ask you to find the volume or the moles or the concentration. So I could be like, what is the concentration of, or how many moles or how many grams are in this solution or whatnot. And again, like I just said, I can have you find the mass. And anytime I ask for a mass in a solution, that means you're going to have to do some type of mole conversion because molarity is in moles, but mass is in grams. And how do you do that? You use the molar mass from the periodic table. So examples 9 and 10 are the two types of questions I can kind of ask you regarding molarity. I'd like you to go ahead and try them without me first. So go ahead and pause it. And then I am going to walk through these. So what is the molarity? So I want capital M of a solution that contains 4.50 grams. Notice this is a mass, so I know I'm going to have to convert it to moles. So I actually over here went ahead and converted it to moles of potassium phosphate in 250 milliliters of solution. Okay, so I know I have to convert this to moles, and I know I have to put this in liters because molarity is moles over liters. So this one conversion, I've got 4.50 grams potassium phosphate. Potassium is +1, phosphate's -3, so its formula is K3PO4. Those naming and formulas are never going away. So that is 212.27 grams. So I'm doing the molar mass, so that grams per mole. So 4.5 divided by 212.27 is 0.0212 moles. So that's how many moles of stuff I put into this solution. Now I'll put this on the equation sheet, but there's 1,000 milliliters in a liter. Just move the decimal place 3 times. So 250 milliliters is 0.250 liters. You don't have to show me the work for that. So I would just put the moles I calculated over the liters I calculated and get my molarity. So I would be like, it's 0.0848 capital M. Okay. This had 3 sig figs, this had 3 sig figs, so I have 3 sig figs. Example number 10 is kind of the opposite. I want to know what mass, okay, which means I'm going to have to use molarity and get to moles and then to mass of sodium carbonate is present in 75.2 milliliters of a 0.0150 molar solution. So capital M is molarity, so I have molarity. I have milliliters. I know if I'm using molarity, it's got to be in liters, so that's 0.0752 liters. And I want to know mass. So if this is the molarity equation, molarity equals moles over liters. Well, I have molarity, so to plug that in right here, 0.0150 molarity equals, I don't have moles, but I do have liters. So I put in this 0.0752 liters here and solved for moles. So the moles are 0.001128 moles. I want to know the mass, so I just converted that to grams. The molar mass of sodium carbonate, which is Na2CO3, is 106. So I got 0.120 grams of sodium carbonate. Okay, so that one was kind of opposite. Now, the other thing we could do in making solutions is instead of starting with a solid, maybe you start with a really concentrated solution and we need to dilute it. So anytime you see the word dilute, or add water to, and it's something that's already a liquid, you're going to have to use the dilution equation. So anytime I'm adding deionized water to what we call the stock is like a really concentrated one. We call it that because it's usually in the stock room. We're going from a more concentrated to a less concentrated. So anytime you're doing a dilution, you need this equation. M1V1 equals M2V2. That's molarity 1 times volume 1 equals molarity 2 times volume 2. So it's like your starting stuff or your stock and your ending stuff, okay, or your new solution. And that's how you use it. You just plug it in and solve for what you don't have. So if you look at this picture here, this is how I would make a dilution. Say I start with this concentrated stock. Notice it's very dark blue. I would measure out using a pipette, or a lot of the times we will just use a graduated cylinder to get out what you need from the stock solution, put it into a new volumetric flask, whatever you're making now, and then you're going to filter that line with DI water. So instead of starting with a solid, we are starting with a concentrated stock solution. So if I said, tell me the steps, you would say, measure the stock, however much stock, using a graduated cylinder or a pipette, put it in a blank milliliter volumetric flask. So in this case, I'm making 250 milliliters, so I want a 250 milliliter volumetric flask. Fill to the line with deionized water. That's it. All right. So calculation wise, I could be like, well, how much of the stock do I need to make this solution? Or what volume can I make if I have this much? So example number 11, I want to know final concentration. Example 12, I also want to know new concentration. So read carefully, but I would try 11 and 12 on your own and then check. So 11 says, what is the final concentration? So that would be like M2 of the solution if 25 milliliters of a 2 molar sodium hydroxide. So notice these go together. Volume of this molarity is diluted. That's that word that told me I need to use M1V1 equals M2V2 to 500 milliliters. So this would be my V2. So you just plug in 2 molar, 25 milliliters equals M2 times 500 milliliters. Now you'll notice I did not convert these to liters. As long as they're in the same unit, you're fine. You do not have to. Solve for M2. My new concentration should be 0.1. Oh, it should be 0.100 with significant figures, capital M. That would be my M2. So it's just a plug and check. Now, example number 12, you have to read very carefully. Okay, what is the new concentration? That tells me it's going to be a dilution of a sodium hydroxide solution if 5 milliliters of a 0.04 molar, so these go together, V1 and M1, is added to 15 milliliters of distilled water. Now, V2 is my new solution, not how much water I added. So V2 is actually 20 milliliters. So you'll notice I added 5 and 15. So read carefully. My V2 is going to be 20. So my new molarity is 0.010 molar. Now, I mentioned using a pipette or using a graduated cylinder in the lab. A lot of the times we'll just use a 10 milliliter graduated cylinder because those are actually pretty precise. But we can also use pipettes. So you'll see these in the back of the lab as well. Volumetric, there's that term again. We use volumetric things when we make solutions because they're very precise. A volumetric pipette works like this. You kind of fill it to the line. It's got like a thing that you put on the end and it sucks up the liquid. And so if it's a 25 milliliter volumetric pipette, if you fill it to that line, that's 25 milliliters. Then you can just add it to your new, whatever you're making your solution in, your volumetric flask. And then what you do is you just kind of let it drain. And when you use this, you're going to have a little bit of solution left in the tip, and that is actually calibrated to be there. So don't try to like use your mouth and blow it out or force it out or anything into the flask. You just let it fall into the flask, and then it's exactly 25 milliliters. Okay. You can also use a Moore pipette, but these are very difficult to use. I do not recommend it. You can use this to measure different amounts, like 1 milliliter or 2 milliliter, whatever, but you really have to be careful with your markings and when you start and stop it. So these are kind of difficult, which is why we stick to graduated cylinders a lot of the time. Now to go just a little bit further into the concentration thing, we can also figure out ion concentrations. So especially when we're working with net ionic equations, I might want to know just the concentration of one ion in there, not the whole compound. So for example, when I put calcium chloride into solution, this is soluble, it turns into Ca2 plus and 2 chlorides. Okay? So thus, if I have a 0.2 molar calcium chloride, well, if this dissolves, I'm actually going to have twice as many chlorines as I have calcium. So when I dissolve this, I would have a 0.2 molar calcium, but I would actually have a 0.4 molar chloride because it's double. This is a 1-to-1 ratio, and this is a 1-to-2 ratio. So every time a calcium chloride dissolves, it looks like this. I get a calcium and I get 2 chlorides. So this would have a 0.2 molar concentration, but chlorine would actually be 0.4. So example here, I've got 0.050 molar of K2SO4 would have, there's 2 potassiums each time. So it'd be 0.1 molar potassium and 1 sulfate. So it'd be 0.050 molar. So you do have to account for those subscripts. This is polyatomic, so it stays together. But if I want to know about just one ion, that's like a component within, you have to account for that subscript, or when it breaks up, what that coefficient is.